Okay, welcome everyone. I'm Alessandro Di Federico, and Anton today, he's here with me. He is the main author of this work. Thanks for coming. So first, a couple of words on who we are. We are from Revenge Labs, a company that I co-founded, and we are building a decompiler that is based on QEMU and LLVM. As you might understand, those are two technologies we like a lot. But on the side, we're also doing consultancy on compilers, simulator, and dynamic binary translation. So today we're here to talk about a bit emulation. There are mainly two ways in which you can emulate, or let's say an ISA, a CPU. You can either write an interpreter where you have a C function for each instruction of the ISA, or you can write basically a small JIT compiler that translates instructions for the guest into instruction to the host, maybe using an IR, an intermediate representation that enables you to decouple things a bit. Turns out that in QEMU, if you want, you can do both. For what concerns the interpreter approach, you can basically write helper functions that are just C functions that are invoked at runtime by QEMU, or you can use TCG, which is QEMU's basically JIT engine. The topic of this talk is basically to automatically be able to go from the first option to the second one using LLVM. Specifically, I mean that if you have a helper function such as this one, which is a simple, let's say, a simple C function that takes two vectors in input and an output vector and just sums all of the elements in the vector, in this case 128, which basically you can imagine implements a vector add instruction, turn it automatically into a piece of C code that you can embed in QEMU that will emit a tiny code instruction, which is basically the intermediate representation that QEMU uses for its JIT engine, and just emit a symbol gvec add, which will perform the addition, and then the JIT compiler will emit the corresponding code. So brief outline, basically we'll do some background, and we will present the two approaches we've got for this effort. The first one is IDEF parser, and the second one, the one using LLVM, is helper to TCG, and then demo benchmarks and summary. So our original goal, since we're working with Qualcomm, was to write a fast open source emulator from the Hexagon DSP. The Hexagon DSP is a well-IW CPU, so you can run basically instruction packets. Each instruction, there are like more than 2,000 possible instructions just for user mode. And if you want to impress your friends, you can show them this packet, which is basically implementing a single packet, the inner loop of the fast Fourier transform. We already spoke about this a couple of years ago. So we refer to that talk if you're interested in how to handle a well-IW architecture and all the specifics of Hexagon. But yeah, let's focus on the predicated add instruction that we have that we have in Hexagon. If we want to write it as a helper, we will have something like this. We have basically an argument for the predicate, and two arguments for the operands of the predicated add. And basically, at the beginning, we check the predicate, selecting the least significant bit. And if it's turned on, we perform the addition. Otherwise, we do nothing, and then we return the result. In tiny code, we will have something like this. We will have an AND instruction that takes the predicate, it ends it with 1, saves it into a local variable, and then performs a branch conditional, checking whether lock is equal to 0, and then jumps to label L1 that we will bind later, and basically skip the addition. So if the condition does not hold, we just add R1 and R2 and save the result into R3. Or if you want to be a bit smarter, you can use a conditional move, because tiny code, the IR of QEMU, also have a conditional move. So you can perform basically the addition unconditionally, so you always perform it, but then you decide to write into R3 the result only if the condition that you want to verify holds. But you don't actually write tiny code directly. You have to write basically a piece of QEMU, which is called tiny code generator, and basically emit this instruction. So very briefly, you can see that here we're creating a new variable. We are emitting an AND instruction, creating another variable, emitting the add instruction, and here we are emitting the move conditional. So this is what we want to emit. So, but in practice, what is the difference between these two approaches? In order to understand it, we can look at the instruction the CPU, the host CPU, so let's assume that you're running QEMU on x86-64, is actually running. So let's consider again the predicated add instruction. This is how we encode it in Hexagon. If P0 R3 equals add R1 R3. And this is what you get if you use the helper approach. As you can see, there are some loads from at offset from RBP, which contains a pointer to the CPU state. Here we are loading R1, R2, and we're loading P0. And then we perform a call. We perform a call to the helper function that we defined before. And this function here has been compiled at build time by GCC. And GCC, by the way, was smart enough to use a conditional move. But this function is not, let's say, handled by the JIT at runtime. It's just a function that we compile at build time. So we compute the function, and then we store the result basically back into the CPU state. If we do it the TCG way instead, it's basically the same thing, but there's less, moving things around register to pass things to the helper function. We load stuff from the CPU state, perform again the conditional move and the addition and everything, and store back things to the CPU state. But now, in order to really appreciate what is the difference, maybe it's interesting to make an hypothesis and say, okay, let's suppose that all the operands of this predicated add are actually known at translation time. So right before that instruction, you have, let's say fixed values for those. In the helper option, you get exactly the same code. But if you use TCG, well, TCG has a mid-end optimizer that is smart enough to constant propagate everything, and you end up with just two instructions that just update the CPU state with the right values. This would just to give you a taste of why is it beneficial to go the TCG way. So to recap, helper functions, very easy to implement. If you know C and you know the semantics of the instruction of an ISA, you can implement it. But it's kind of slow because you have the hover for the calls, and basically you cannot perform any optimization at translation time. On the other hand, if you go the TCG route, it's fast, but it's also kind of tedious. You have to understand TCG, and it has its quirks, and I would say it's kind of a barrier to entry to support new architectures. So it has its own limitations. So why don't we generate this stuff? Why don't we go directly from a helper function to generating the piece of front end, the piece of TCG that we need? So our first attempt at this was idefparser. So this is specific to Hexagon. And here on the left, you can see what basically the good Qualcomm guys give us, what we call the source of truth, which is a pseudo-C language that basically describes the semantic of an instruction. As you can see here, we have the description of the predicated add instruction. We have some input registers, the predicate register, this is the output register, and the two operands register, or the operands of the add. And we just have if the lowest bit of the predicate is turned on, then perform the addition, otherwise cancel, ignore cancel. It's a quirk of basically the Hexagon thing. And that's it. So our idea is, why don't we write a small compiler that goes from this source of truth directly to the TCG? And that's what idefparser does. Idefparser is a built-time tool that takes this input and outputs something like this. So you take the header of the source of truth and emit the header of the C function, part of TCG, and then here really quickly, when you look at the condition, we emit the code to basically emit an extract, which is similar to an end. Then we handle the if statement itself by emitting a label, generating a conditional branch, and then we emit the body of the then branch of the if statement by emitting an add, a move, and so on. And then, yeah, we handle the else, emitting some labels and some branches. So this is what idefparser used to do. Now, this was written in Flex and Bison. It's currently upstream and maintained, and it brings some good results. It supports more than 1,300 instructions for Hexagon, but it has some downsides. Specifically, this is really tightly coupled to the source of truth that comes from Qualcomm. So it's basically can only be used with Hexagon. And also there's no AST, there's no IR. This is basically a syntax-driven compiler, very straightforward Flex and Bison syntax-driven compiler. But most importantly, basically we had to implement a poor man's C compiler, which is something I do not suggest people to attempt. So we thought, why write a poor man's C parser when we can use a real compiler, right? And after all, tiny code is an IR, and compilers, C compilers often use an IR. So why not translate IR to IR? And this is what helpers to TCG is about.
So exactly as Alessandro said, instead of going from pseudo C code through idefparser and ending up with TCG code, why don't we start with C code, feed it through clang to end up with LLVM IR, the IR of clang and LVM, and then feed it through our helper to TCG tool to translate it directly to TCG code. This brings us 4 main benefits. Firstly, again, we don't have to write a poor man's C front end. And then it turns out that translating an IR to an IR is much simpler than like a pseudo C language to an IR. And by relying on LLVM, we're also able to use a lot of built-in optimizations that exist already, and we're able to write our own optimizations on the IR. And finally, this allows us to create a tool that is completely architecture independent and can be used outside of Hexagon. So I want to spend a little bit of time introducing you to LLVM IR in case you haven't seen it before. We have our predicated add example here on the left again. And now I'm going to go through like a mapping between C code and LLVM IR. So we can see that the header of the function is pretty much it's very similar. We have our integer types as i32s, and we have our registers as arguments again. The first thing we encounter is an instruction which is not present on the left-hand side. This is an alloca instruction which creates a local stack variable which we need to store the result. We'll see it in a little bit. But then we continue on and we compute the AND with 1 to get the least significant bit again. We perform an icomp instruction which compares against 0, and then we branch on this result to either the if label here or the exit label. In the if branch, we perform the addition and we store the result. And in the exit label, we simply load the local stack variable and we return it. Now, say we want to just manually translate this to tiny code to see what it would look like. We start out with the alloca and store. We can simply map this to a move to a local variable. Then the AND instruction can be mapped to an AND in tiny code. The icomp can be mapped to a set condition. The conditional branch in LLVM can be mapped to a conditional branch in TCG or tiny code again. Labels map directly to labels. And similarly here, we can map the addition and store to an addition and move. And then we finally branch to the exit label, and we load our results into the destination register. So the mapping between LLVM IR and tiny code is pretty much one-to-one in most cases, and is rather easy to perform. So I want to spend a little bit of time focusing on the helper to TCG pipeline. We're going to be looking at a lot of LLVM IR, so I hope this introduction helps a little bit. So again, the point is we start from C code, we go through clang 0 without optimization to end up with LLVM IR. We feed it through our tool, and to finally get TCG down here. Let's consider the predicated add example again from Hexagon. And this time it's written as a simple C function that can be included as a helper if you want to. We go through clang, we end up with a lot of LLVM IR, you don't have to focus on it. The only thing you might notice is that it has the same high-level structure as the C code. You have some setup code, some branching, you have an if block and an else block, and then you return. Once we enter our tool, we firstly go through a simple like filtering phase where we remove instructions we don't care about, we remove attributes we don't care about. This is not super relevant for this talk. We then go into a simplification phase which runs a few LLVM IR passes or LLVM passes and a few of our own. And this is where you start seeing the real transformations to IR. So the code has been simplified and we can now start performing a bunch of optimizations on it. So after this, we go into a small vector transformation pass. This is not something we really touch on here, but we do a bit of loop optimization ourselves and perform some loop canonicalization. After this, we go into a O3 pass, which is the bulk of the optimization. And here you can see that we ended up with an AND instruction, a comparison, addition, and a select, which is very close to what we saw previously. Afterwards, we go into an instruction combining pass that we wrote ourselves that combine, if you go back again, we take the icomp instruction and the select instruction and we combine it to a move condition. This is something that just maps easier to tiny code. We also do a little bit of basic register allocation and such to get prettier looking IR in the end. So after this, we go into the backend, which emits the following tiny code. And now we can see again what we saw in the beginning. We perform an addition, an AND, an addition, and a move condition. Compare this to idefparser where we had to emit an actual branch. So what about vector instructions? Vector instructions are something that's very easy to write in C code and can often be quite annoying in tiny code. So let's take a look at the example we saw in the beginning, performing an addition of bytes, 2 vectors of bytes. Once we go through clang to LLVM IR, we end up with a lot of code, which is, again, you don't have to focus on this too thoroughly. We go into the filtering phase and then simplification. Gets a bit easier. Here it has the same high-level structure as the C code again. We see a loop header and then a loop body, which performs the addition of each element. After our small vector transformation and our loop optimizations, we end up with a bit more normalized, more normalized loop. We have extracted some induction variables. After this, we go into O3, which does the bulk of the optimization. And you can see here that we end up with a single instruction in the middle, which is a vectorized and add instruction. And this is possible due to the autovectorizer of LLVM. So we go into inst-combine, doesn't do anything in this case. We go into the backend, which performs the mapping to TCG. And in the end, we end up with a single vectorized add instruction. So at this point, I want to spend a little bit of time showing you the actual tool and how it works. So I want to do a small demo. Oh. So we'll see how this goes. So on the left-hand side here, I have a C file. And on the right-hand side, I have an output C file. I have a small script that I wrote called, let's see if I can find it there, run translator. It firstly runs clang to produce LLVM IR. It then runs our helper to TCG tool to produce the TCG code. So if we go back here, we have, again, our simple C file. We can just start typing. So say we want to write an add instruction. We can do, oh, I'm not super used to this keyboard. We can do something like this. If we now run our translator, which I've mapped to F, or to save actually, it should run, I think. Yeah, and we get, I think we get nothing on the right-hand side because we need to attach an attribute. So the way we do that is we add an LLVM attribute, and this is how we tell our tool that this is a function that we actually care about translating. So if I typed everything correctly, looking sideways, this should work, and we should end up with some output code. Which we don't, which means I did something wrong. Typical, okay. No, the close parentheses are fine. Okay, this is interesting. I did not expect this. So what does it say here? It might not have saved, you say, okay. It should be fine. We can do this. So okay. Oh my god, okay. And then we okay. Yes, okay. There was something related to saving on the file. Thankfully. Okay, so we end up translating the file. Here we perform an addition, and we get an addition in TCG. And the thing here that's fun is we can open them both. We can say change the addition to a subtraction, which let's see if this works. Again, I set it up to do it automatically. You can see now that it maps the addition to a subtraction, which is what we expected. We can again do other interesting things, such as mapping it to, I was going to show an absolute value also. If you perform a Turner expression, it will map to an absolute value. Don't really have the time for that, sadly. I have a few other examples prepared, which are vector examples from Hexagon. Here we have an instruction that performs, again, a vectorized add of 128 bytes, but it saturates also. And in this case, LLVM is clever enough to also, let's see if this works. Does it say file exists again? Yeah, okay. I guess we have to do this. Sorry. There. So for some reason I had to restart them. Okay, good editor. So we're able to map the vectorized saturated add to a single TCG gen SS add, which saturates. We have a similar example for another instruction, which, again, vector instruction iterates over all the elements. It takes the difference between the two elements of the vector and then takes the absolute value and stores that to the result element. So we're getting towards a bit more complicated instructions. I'm going to preempt this, and I'm going to restart Vim. Then we run it. It runs. There. Okay, so in this case, we end up again with a bit more vector instructions. We start by performing a comparisons between the two vectors to figure out which element is smaller in each of the elements. We then perform both subtractions. We should subtract, say we have two elements A and B, we subtract A minus B and then B minus A. That's what we do in this subtraction and that subtraction. Then we perform a vectorized bit select operation to get the final result. So at this point, we can start returning to the presentation. I want to go into a bit of benchmarks, because we did want to, well, the main motivation here is to try to compare our different implementations that we have. So we have our TCG implementations produced by idefparser, and also the ones from helper to TCG. And then we have, of course, the normal helper functions. So we want to compare these somehow. We started out by running some just normal general purpose benchmarks, which you can see right here. So the figures are the speedups relative to QEMU Hexagon compiled with helper functions and a few manual overrides, manual TCG implementations for things such as loads and stores. So in this case, we see roughly 2 to 3 times speedup, which is pretty good in both cases. There's not a huge difference between idefparser and helper to TCG. Helper to TCG is a little bit faster, but not by a long shot in this case. So here you also have to keep in mind that these are general purpose benchmarks. They don't necessarily exercise all of the Hexagon instructions we emit, and we already have manual implementations for a lot of the loads and stores. So the next thing we wanted to look at is, well, okay, can we get some sort of metric on the quality of the code we emit? And here we thought of looking at the host instruction count, runtime host instruction count for a few tests. So here we're looking at a neural network test for Hexagon and also a corner detection test. And the numbers you see here are the percentage reduction in instruction count compared to our baseline, which is again QEMU Hexagon with helpers and a few manual overrides, manual implementations. So for idefparser, we see a 1.5 to 3% reduction in the instruction count, and for helper to TCG, we see more like 10, 11%. So we're actually reducing the work that the computer has to do, which is pretty good. The next thing we wanted to do is we want to get a better measurement of how an individual instruction performs. And our methodology here was to auto-generate a lot of tests that try to stress a single Hexagon instruction. And what you see here is there's a lot going on here, so I'll try to explain it. On the x-axis, so all of these individual dots represent a single Hexagon instruction. So for instance, we see this dot and say that dot are the same instruction. The orange line is for the helpers. The blue line is for helper to TCG. On the y-axis, we have the absolute execution time. And what we can see is that, well, our blue line is mostly below the orange line, which is, ooh, good. And if we start extracting a bit more maybe interesting data, we can look at the geometric mean of the speedups, and we get roughly a 4 times speedup. If we look at these, say, peaks, like we compare, say, this instruction to this instruction, we see roughly a 30 times speedup. And keep in mind that these are individual instruction tests and can be seen as more of a, like a maximum speedup that we can expect, maybe. So, oh, yeah, okay, I mentioned this roughly. So we see an average speedup of 4 and a peak speedup of roughly 30. So at this point, I want to start rounding out the talk. So to summarize, we've created a tool called helper to TCG. It's a build time tool relying on Clang and LLVM that's designed to take helper functions to TCG functions in an effort to help implementers, like make it easier to create a new front end. And this is primarily also a tool that is architecture independent, meaning if you have a helper function, you should be able to slap an attribute on it, run it through the tool, and get TCG code out. We applied it to Hexagon, where we were able to emit at the current state, we're able to emit 1,400 instructions. The eventual goal here is to entirely replace idefparser. And importantly, we emit more efficient and smaller TCG code as compared to IDEF parser. And finally, we're able to handle more complicated instructions, such as vector instructions, which IDEF parser has no chance of being able to translate. And this is something that we plan to upstream, so keep an eye out if you're interested. So at this point, I just want to extend a big thank you to you all for listening, and I also really want to thank Qualcomm for sponsoring this project, and in particular, I want to thank Taylor for all of his work that he's been doing on the QEMU Hexagon frontend. Thank you.
Thank you. Excellent work, by the way. So 2 quick questions.
Yeah.
You sort of glossed over, originally with the IDEF parser, you're working with the pseudo-C that's in the Hexagon architectural manual,
Yep.
but this works on plain C, so how do you bridge that gap? And secondly, how much work is it to tell your LLVM stage about new TCG ops when they get added?
I didn't understand your last question. How much work is it to tell? Sorry.
So if we add a new TCG op
Yeah.
to do another particular operation, how hard is it to inform your code generator that it exists and be able to integrate it and take advantage of the TCG ops?
Okay, I get it. So I'll answer your first question first. So the difference between the pseudo-C and helpers is it's not that difficult. Like the pseudo-C is close enough to just normal C that we're able to just easily bridge the gap. We have a Python script that takes the instruction definitions that we get from Qualcomm that generates either the pseudo-C or the helpers, but there's not a lot to it really. There's no real difference, you know, in terms of semantics.
Okay, well, a couple of regexes and some replacement text.
Yeah, pretty much. As for the second question, say you were to add a new TCG op, the thing with our LLVM approach is that it's very easy to just like map it to new things. Like it's easy to say, okay, if we say we have a pattern of an addition, or say we do an, so one thing we did with the MoveCon is we look for patterns of comparisons and then set cons, and then we just map that to a MoveCon. And this is very easy to do with the tools that LLVM gives us. Very straightforward.
All right, thanks.
Thanks for the great talk. When you parse the LLVM IR, like how stable is that format? Do you anticipate you're going to have to constantly chase LLVM, or will you upstream your code into LLVM perhaps?
We don't plan to upstream it into LLVM. There's a little bit of chasing that you have to do. We currently target like 4 or 5 versions of LLVM. They make a few changes every now and then to say how pointers work, which we will have to adapt to. But we'll cross that bridge when the day comes. So
Okay, fair enough. Thanks.
Okay, thank you.